Let's first consider continuously compounded interest. So we're going to look at the time rate of change of amount of dollars in a savings account. So here's the situation. At time t equals 0, which we will call t naught, Jack puts $1,000 in a savings account at a certain interest rate, compounded continuously. And Jill, at the same time, puts $2,000 in a similar savings account at the same interest rate. At another time t equals 2, and this we'll call time t1, t1 will equal 2, Jack and Jill went to the bank to see how much money each of those savings account had. Now, you have to realize that this bank that we're talking about is on a hill. So Jack and Jill actually did go up a hill. So let's look at a table. There were two savers, Jack and Jill. At time t naught, which was 0, at time 0, Jack put $1,000 into his savings account. Jill put $2,000 into her savings account. Now, after some time, at time t1 equals 2, Jack will have, let's say, $1,040 in his account. So that means that in the time from t0 to t1, Jack's account went from $1,000 to $1,040. So the increase of money in his account was $40. Now, we would like to, just from this information that we have up here, which is shown in this table, we would like to figure out how much money Jill had at time t1, and also what was the increase in the number of dollars that she had. You might think that we'll calculate this one first and then calculate the difference to get this, but we're actually going to do it in reverse order. We'll see in a minute that it's easier to calculate this quantity first and then go back to figure out what that makes this quantity equal to. So looking at that table, let's fill in a couple of numbers. The numbers in black here we've already had. So let's first of all see how we computed this 80 in the increase in the savings account for Jill. Well, let's see. Over a period of time, Jack started with 1,000, he got some interest, and that gave him 40 extra dollars. Jill started with twice as much money as Jack, and so she should have an increase twice as much as Jack. So instead of 40 as Jack had, Jill's take would be $80. Well, if this is 80, the increase in her amount, and if she started at 2,000, then A of T1 must have been 2,080, so that the difference of these two will give us the 80 that should be here. So just looking at what's in this table, we can write down the following. The amount that Jack had in his account at time t1 minus the amount that Jack had in his account at time t naught divided by t1 minus t naught is going to be 40 over 2 minus 0, which is 20. For Jill, a similar calculation, the amount that Jill had at time t1 minus the amount that Jill had at time t naught is going to equal, divided by t1 minus t naught, is going to equal 80 divided by 2 minus 0, which is 40. I used the fact that we were letting t naught be 0 and t1 be 2 in this example. So that tells us that the average rate of increase in the amount in Jack's account over that time period is 20, and for Jill, similarly, it's 40. So what we notice now is that at the beginning, and actually at any time t, the amount that Jill has in her account is twice the amount that Jack has in his account. And we also notice from the computation up here that the average rate of change in Jill's account is twice the average rate of change in dollars in Jack's account. So when we doubled A, we doubled the rate of change, delta A over delta T. So since doubling this doubles that, that tells us that the ratio, the change in A over the change in time, is proportional to A. Let's call that constant of proportionality R. And so this relationship of proportionality can be written as the change in A divided by the change in T is equal to some constant times A. So we had the average rate of change of A with respect to time t is a constant R times A. If we looked at this equation at two different times, t0 and t1. If we let t1 approach t0, then this average rate of change becomes an instantaneous rate of change, the derivative of A with respect to t. This other side just remains R times A. R is a constant here. R is a constant of proportionality. We know how to solve this type of equation because this equation is separable. If we divide both sides by A and multiply both sides by dt, we can rewrite the equation as dA divided by A equals R dt. Then integrate both sides of this equation, and the integral of dA over A is natural log of A. The integral of R dt is RT plus a constant of integration. So that tells us then, if we take exponentials of both sides here, that A is equal to E raised to the RT plus C power, which we can write as E to the C times E to the RT, just using properties of exponents. And now let's call E to the C, let's call it A0. So we finally have that A is equal to A0, some number A0, times E to the RT. We have then solved this differential equation, and the solutions look like A equals some constant A0 times E to the RT. A is going to be growing exponentially in value. So let's look at this equation a little bit further. Suppose we look at what happens at time t equals 0. Plug a 0 in for the t's here. A of 0 is A0 times e to the 0. But remember that e to the 0 is equal to 1. So this is just A0 times 1, which is A0. So that tells us that the amount in the account at time 0 is A0, the initial investment. So that tells us how to interpret this A0. It's the initial amount invested in the savings account. This R up here is going to be called the interest rate for the continuous compounding. As an example, let's suppose that Jack put $1,000 in savings account at 10% interest rate R compounded continuously. How much would be in the account after 1 year? So in that case, this A0 is going to be 1,000. This R up here is going to be 10%, which is equivalent to 0.1. So in that case, we have, starting with this equation, A of t equals A0 e to the RT. So A of 1 is going to be the following. A0 is 1,000, then E to the R, which is 0.1, times T, which is 1. So what do we have here? We have 1,000 times E raised to the 0.1 power. If you punch that into a calculator, you'll find out that that is $1,105.20. So in that 1 year period, your interest was $105.20. You started with $1,000. After 1 year, you ended up with 1,000 plus 105.20. So this is your interest. And so that tells us then that the annual percentage yield was 10.52%. We gained $105.20 from our initial $1,000 investment, and that is an increase of 10.52%. So notice the interest rate R was 10%. The annual percentage yield was higher, slightly higher, 10.52%. So each year you are getting actually 10.52% more than at the end of the previous year. In the previous example of continuously compounded interest, we saw that the amount in the savings account increased exponentially. Now let's talk, so we had exponential growth in that account. Let's look at another example of exponential growth, the growth of some sort of population. On the internet, there are some sources that indicate that most types of bacteria populations can double their size somewhere between every 4 to 20 minutes. To get a constant increase over time, constant rate of increase, we're going to assume that the growth rate, which is going to be a constant, depends on the type of bacteria. Some bacteria grow faster than others and divide more quickly than others. And it also depends on the environment that they are in. To let the rate be a constant, we're going to assume that the environment is really nice. It's as conducive to replication as possible. You have good temperature for the bacteria, sufficient food, and so forth for all time. And we're going to assume that in this colony of bacteria of some uniform type, we'll assume that each bacteria cell reproduces at the same rate. You might have thousands or millions of bacteria in a culture, but each one of those bacterial cells reproduces at the same rate. That's going to be a fairly strong assumption. So let's let P of t be the population size of a bacteria colony at time t. And the size of the bacteria colony could be measured, for instance, by the number of bacteria cells or the weight of the bacteria culture. If the population size is large, the discrete nature of the population size can be closely approximated with a continuous analog. You can have 1 bacteria, 2 bacterial, 500 bacteria, but you can't have 43.7 bacteria cells, okay? But if we have a huge population number-wise, number of bacteria, we can approximate the discrete situation by a continuous model. So here's what we're going to do. Here we're letting P of t be the size of the population of bacteria. We're going to use assumptions for P of t very similar to those that we used for A of t, the amount of money in a savings account. We're going to assume that the time rate of change of the population size P of t is proportional to the size of the population. That is, the derivative of P with respect to t equals some constant of proportionality K times P. P of t is a function of t here. Okay, so what happens is that P, population size, plays the same role as amount of money in the bank if you're looking at continuous compounding. So our model becomes the following. The population size P of t should satisfy this ordinary differential equation, dp dt equals k times p. And we can solve this equation the same way as we did in the continuous compounding situation. But for variety, let's solve this equation a different way, using integrating factors. So let's see what we can do. We start with the differential equation, dp dt, the derivative of population size with respect to time equals k times p. Subtract kp from both sides, and we can write the equation as the derivative of p with respect to t minus k times p equals 0. For the integrating factor, this is a first order linear differential equation. The integrating factor mu of t is going to be e to the integral of this function right here, which is a constant function, minus k times dt. The integral of minus k dt is just minus kt. So the integrating factor is e to the minus kt. So what do we do with this integrating factor? We multiply both sides of this equation by that integrating factor. So we get e to the minus kt times dp dt minus k times e to the minus ktp equals that integrating factor times 0, which is still 0. Now let's remember what made that integrating factor special. These two terms here can be written as the derivative with respect to t of the integrating factor times our function p of t. So the derivative with respect to t of this stuff equals 0. Integrate both sides, and we get this stuff is the integral of 0, which is just going to be an arbitrary constant, which we will call p naught. So e to the minus kt times p of t equals this constant p naught. Multiply both sides of this equation by e to the kt, and we finally get that p of t equals p naught e to the kt. Once again, this p naught is going to represent the size of the population at time 0. So we saw that the solution to this differential equation is p of t equals p naught e to the kt. If we plug in 0 for the t's here, what we get is p of 0 is equal to p naught e to the 0 times t, which is e to the 0. E to the 0 is 1. So what we get is p of 0 is just this constant up here, p naught. P naught is the population size at time t equals 0. We're assuming that our population grows in size, so that constant k that we see here is going to be some positive constant. So let's consider the following problem. At time t equals 0 years, the bacteria culture has 1,000 cells. After 1/2 minute, it has 1,100 cells. When will the bacteria culture have 2,000 cells? So in our solution, let's let p of t be the number of cells after t minutes. In that case, p of t is given by p naught e to the kt, which is 1,000 e to the kt. We know that the p naught here is the initial size at time t equals 0 of that population, so we know that's 1,000. That's given to us right up here. The culture has 1,000 cells at time t equals 0. We still need to find k. Well, what do we know? After 1/2 minute, it has 1,100 cells. So let's measure time t in minutes here. So after half a minute, the culture has 1100 cells. So P of a half has to equal 1100. But let's remember that P of a half by our formula here is going to be 1000 e raised to the k times a half power. So e to the half k then has to equal 1.1. All we did was divide both sides of this equation by 1000. Take natural logs of both sides. Then 1/2 k is equal to the natural log of 1.1, and multiply both sides by 2, and you get that k is 2 times the natural log of 1.1. Punch this into a scientific calculator, and you'll find out that it's about 0.1906. So that tells us what the value of k is here. And we can plug it in here to get 1000 e to the 0.1906 times t, which will give us the number of bacteria cells at any time t. In our particular problem, we want to know when the culture has 2000 cells. So we still have to do a little bit more computation. So far then, we have that P of t is equal to this, which equals 1000 e to the 0.1906 times t. So when does the population double? Let's find the time t2, the doubling time, satisfying P of t2 equals 2000. So we have 1000 e to this constant times t2 has to equal 2000. Divide both sides of this equation by 1000, and we have this exponential has to equal 2. Take natural logs of both sides of this equation, and we have 0.1906 t2 is the natural log of 2. To solve for t2 here, divide both sides by this constant factor. So t2 is equal to the log of 2, natural log of 2, divided by 0.1906. Punch that into a calculator, and you'll get approximately 3.637. So after about 3.637 minutes, the bacterial population size will be 2000. That solves our problem. Here's a graph explaining the situation. Here we have plotted that exponential function p of t, which was 1000 e to some constant times t. And we wanted to know when the population hit 2000 bacteria. So come over here to the vertical axis 2000, go across horizontally till you get to the curve, and go down. And here we can see that the corresponding t value, this axis is basically the t-axis, this vertical axis is the population size, p of t axis. T is going to be about, what, 3.246, a little bit more than 3.6, which agrees with what we saw in our calculation. This population growth model that we looked at has some limitations. Since the rate of growth of the population is assumed to be proportional to the population size, we can see that it implicitly assumes that the size of the population has no effect on its ability to grow. Many populations, on the other hand, in real life, have limited resources of food, water, and other things. Also, our model does not take into account deaths. Maybe we should be looking at a birth-death model instead. So limited resources can restrain population growth, and there might be an upper bound on the future size of the population. There's only so much food to go around, and if the population size gets too large, people might start to starve. Here is a graph of the US population size, and the data comes from the US Census starting, I believe, in 1790 and going through 2020. If we look at this graph of the population size, it looks like it's more or less exponential. There are a few places, such as right here, where the curve seems to do something slightly different. But exponential growth would probably be good for modeling the US population, at least up until the current time. It seems that we have not run out of food and other resources that would limit population size at this stage. Here is another example of the population as a function of time, going from about 1790 to I guess a little bit more than 2050 on the time axis, number of the year, and on the vertical axis we have the size of the population, and each of these numbers is multiplied by 1 times 10 to the 9th. This sort of model gives us an equation that looks something like this, and it's called a logistic growth model. The equation for it is slightly more complicated than it is for just simple exponential growth. But if we look at this curve, this point right here is at 1790, the year 1790, and the population here is about 54 million. Kind of hard to tell from this graph, considering these numbers are given in billions up here. But in any case, as the years go on through the 1800s, the 1900s, 1950, out to the 2000, the population reaches or approaches a limiting value out here of, it looks like, about 1.4 billion. What's happening is in the early years there's lots of room for growth, lots of food for the small size population, but as the years go on the population grows and maybe the food supply doesn't, because there's only a finite amount of land for growing produce. So as time goes on, food can become an important criteria for how large the population gets, and in this particular graph the population kind of levels off at 1.4 billion because there's just no more room for growth. One of the resources for increasing the size of the population is not growing, and so the population itself cannot grow. Another thing that could happen, not with the logistic growth model, is that the population could actually go down after a while. This is happening in some countries' populations now. As the population becomes more educated, the number of births per person tends to decrease, and so much so that in many countries it's beginning to become clear that population sizes are about to decrease rather than increase. They are already showing a tendency to decrease. So now let's look at the radioactive decay of some element such as tritium. Spontaneous radioactive decay, we don't look at having a chain reaction here, just each atom of this radioactive substance can decay at a time or not. Let's let N of T be the amount of radioactive substance left at time T. And here's the situation we're going to consider. At time T equals 0 years, we have 5 milligrams of tritium. It decays radioactive because it's radioactive. The half-life of tritium is about 12.3 years. When will only 2 milligrams of tritium be left? Okay, well here, instead of the amount of tritium increasing, the amount of tritium decreases. And what we can say about this situation is the following. If we let N of T be the amount of radioactive tritium left at time t, then the derivative of N with respect to t is going to equal minus some constant k times N of t. dN of t is negative since we're going to have N decreasing. And we'll put a minus sign here, and we'll assume still that the k is positive. So minus k right here is a negative number. So this product, minus k times n, is a negative number, which makes this derivative a negative number. Okay? So this looks very much like the equations we solved before, except we have this extra minus sign right here. Going through an argument very similar to population growth, we get that N of t equals N naught e to the minus kt. N naught is the amount of, in this case, tritium measured in milligrams at time 0. Well, the half-life of radioactive element, we'll call that T sub 1/2. It's the amount of time it takes for the initial amount of radioactive element to shrink by a factor of 1/2. So the amount of tritium we have at this particular time is 1/2 the amount that we had at time 0. We want to solve this equation for this T sub 1/2. So in this problem, the tritium problem, we are starting with 5 milligrams of tritium, and the half-life is 12.3 years. So the first thing we can do is say, well, the N naught value is 5. I don't know what K is yet. So N of T is 5 e to the minus kt. I would like to find this K. So we'll do that from using our knowledge about the initial amount and the half-life. So N at time T sub 1/2 is 5 times e raised to the minus k times this t value, and that should be half of the 5, 2.5 in other words. Divide both sides of this equation by 5, and we get e to the minus k times that t value equals 1/2. Take natural logs of both sides. We get minus k times this t value equals log of 1/2. So minus k times 12.3 was the half-life, remember, 12.3 years, equals log of 1/2. And log of 1/2 is log of 1 minus log of 2, which is 0 minus log of 2. And so this log of 1/2 simplifies to minus the log of 2. So 1.23 times minus k equals minus log of 2. Solving this equation algebraically, we have k equals log of 2 divided by 12.3, and if you put this into a calculator, you'll see that it's approximately 0.0564. So at this stage we know k. So we have the complete formula for N of t, the amount of tritium at time t. It's going to be approximately 5 e to the minus 0.0564 t. We're now in a position to answer the question, when will we have 2 milligrams of tritium left? So we want to solve N of t equals 2 for the value of t. So substituting what N of t is right here, this has to equal 2. You need to solve this equation. Let's divide both sides of this equation by 5. So e to minus this stuff equals 2/5. Take logs of both sides and then do division. And what we find is that t is minus 1 over 0.0564 times the log of 2/5. If you calculate this value using a calculator or computer, you'll find that's approximately 16.25 years. In about 16 1/4 years, we will only have 2 milligrams of tritium left. The rest will have decayed away to something else. To summarize what we did, we considered 3 models. The first one was continuously compounded interest in a savings account. The second one was population growth. In our particular example, it was bacterial growth. And we also considered a model of radioactive decay, and we looked at the decay of tritium. In all 3 of these models, the ordinary differential equation had this sort of form. The derivative of y with respect to t equals some constant times y of t. And in all 3 models, the solution was of the form y equals y naught e to the ct, constant times t, in this exponential function right here. The c here, that constant, was positive for continuously compounded interest and also for population growth. And when we talked about radioactive decay, c up here turned out to be negative. So all 3 of these models used this differential equation as the model of what was going on, and the solution of the equation for that model, that differential equation, had this form of exponential growth or decay. I hope you enjoyed this lesson, and please stay around for more lessons coming up. Thank you for your interest. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.